Okay, welcome to the first of several lectures here for radiation. So I'll go ahead and write it out here. The purpose of this is to provide you with some modules that cover the material that you need to know for the thermal fluids qualifying exam at Villanova. And to do that, there will be a few of these radiation modules. So I'll start here with the first one. The first one today is we're going to talk about essentially about intensity. So introducing you to what intensity is. Okay, so to start then, let's revisit convection. And of course, with convection, we have Newton's law of cooling. The Newton's law of cooling, write it out, it's going to be the heat flow Q is equal to H times A times delta T. So let's go look at this equation a little more philosophically. So here, of course, Q is our heat flow. H is our heat transfer coefficient. And then you have area and delta T. So what happened back in the early days of looking at this equation when it was first derived, there were some observations. Basically, the observation is that the heat Q will increase as delta T increases. So that was pretty clear and universal. The other one is that the heat flow would increase proportional to area as well. So those are pretty straightforward. But then there's many other complexities that come in with convection, things like the type of fluid, the properties of the fluid, the geometry, the flow rate, and so forth. So the catch-all really comes down to what this value of H is here. So this is everything else is absorbed into H. Right. So the idea there is that you take what looks simple on the surface, but then it boils down to how do you get H? So of course, there's been a lot of work into figuring how to get H, and you use Newton correlations and whatnot, and that's how you end up getting it. Radiation actually has some similarities here. So if you look at radiation, turns out the equation here has some similarities in that we're going to use radiative intensity as our catch-all, kind of like we use H as the catch-all for convection. So here's what it looks like. I'll write it out in all its glory, and what we're going to do is decipher this equation a little bit more here. So we have dQ, which is a differential amount of heat flow, is I sub lambda E, and I'll put all this in parentheses, and this depends on lambda, actually theta and phi. I'll go along with the nomenclature in the Incompare and DeWitt textbook. And there's dA cosine theta d omega. Sorry, d lambda and then d omega. What is this? Well, let's talk about the stuff we do know. And the one thing is that notice that instead of writing out as a full heat flow, it's written out as a differential heat flow. And the reason why is because you have to integrate out both sides. Notice there's no differentials at all showing up in Newton's law of cooling above, but you have differentials showing up in this radiation equation down below. So for our sake of looking at this, let's assume that dQ is some sort of amount, a small amount of heat flow. So then there's this value I. So this is our intensity. So this would be, again, analogous to the heat transfer coefficient. It's kind of a catch-all. And notice that there's a lambda here. This just simply means it's a function of wavelength. So let's talk about that for a moment here. Turns out with radiation, it appears as essentially waves over the electromagnetic spectrum. So we can say that the wavelength lambda, it has units here. We generally like to use microns. And the reason why we do that is because all the actions when it comes to thermal radiation for practical engineering problems shows up in really three areas of the broader electromagnetic spectrum. It shows up here for very short wavelengths. It'll be ultraviolet. And kind of in the middle, it'll be visible. So between 0.4 and 0.7 microns is visible. And then you have infrared for radiation beyond 0.7 microns. The 0.4 would be your violet. Your 0.7 micron radiation is your red. So the idea here is that the radiative intensity, whatever this mysterious value of I is, it does depend on wavelength. So it will vary with this value of lambda. So then we have the next thing here is that we have a theta and a phi, and I'll define those out a little bit more here in a bit. But the idea is that these show that it depends on direction. It's a function of direction. And we're going to do some calculations later on in this module about how you get it as a function of direction. Then there's and this theta shows up here again, but this collectively dA cosine theta is the projected area. Let's take a moment to look at that. If you talk about direction and projected area, suppose we have a surface here, and the surface has some small area dA. So what we do with radiation, we're going to draw something like this pretty frequently here in these modules, is we're going to say there's a normal vector that comes out perpendicular to the plane that dA is in, like so. It's pointing straight up. And say hypothetically, your detector, which I like to draw as an eyeball, is over here. So what you see, if you were to draw a line between dA and your eye, obviously there's an angle here between the normal and then this line connecting the detector and your eye. We're going to call that theta. So the question is that what do you see as opposed to what is the area dA? What you see is a projection of dA. So I'll make this blue. And the idea is that you're not going to see the entire dA. So from your vantage point, you only see part of dA. In other words, it appears as smaller than dA to your eye. So this would be dA times cosine theta. And you can see this because, or you can kind of imagine how this works, is that imagine this dA is a piece of paper. And if you're looking at the piece of paper straight on, it looks, you get to see the full area dA. It covers up your field of view as much as it possibly can. Assuming that let's assume that this distance between your eye, the detector, and the paper is held constant. If you're straight up above it, you get to see the full piece of paper. And if you go all the way down to the side, the piece of paper appears very, very thin. So you don't get to see the field of view as far as the paper compared to your eye is very, very small. So you don't get to see the whole piece of paper. So this is what we mean by projected area. All right. So then if we go back to this equation again, we have the direction. You can see the theta right here shows up in direction. So the idea is that intensity can vary with theta, but can also vary with phi. And I'll talk about that here in just a moment. And that's what this d omega comes into play here as well. So this is a solid angle. So this is a function of something called a solid angle. The last point before I move on, and we'll talk more about this in the second module, is that E stands for emitted radiation. Which means you're producing radiation at a surface. So keep that in mind as we move forward here, as we do a couple of examples. We're talking about radiation is being produced at a surface here, and then it's being detected out here. So let's then take a look at the direction component of this. And this is something that uses a little bit of geometry you may or may not have seen before. So I'm going to go about it assuming you have not seen it. And so let's start by looking at something that I know you've seen, and that is a circle. So let's talk with a 2D case here, a circle. So if you have a circle, use the tool here to draw one. Here's our circle. If you were at the center of the circle and you draw a line, say out to here, and you draw another line out to here, and say this angle here is very small, we'll call it d theta. And the radius of this line is capital R. And that means the length of the arc here is going to be r d theta. And if you integrate r d theta over all of theta, what you get is 2 pi radians in an entire circle. And that's simple enough to do. You just integrate d theta from 0 to 2 pi and you get 2 pi. So in the 3D case, we're going to look at a hemisphere. So you could have basically either a sphere or a hemisphere. And we'll show you how we handle that here in a moment. But to start, let's take a surface again, like we have here, and we'll draw 3 axes like we normally do for 3D. So this first one will be the Z, then we have X, and we have Y. And notice that the normal vector here is pointing along the Z axis. We have X and there's Y. And the idea is let's take a little patch of area that's such that the normal of this patch is pointing directly at the origin here. So here is our little patch. I'm going to draw it out like that, and hopefully that'll work pretty well. And it's curved a little bit. And you'll see in a moment why we do that. All right, so now let's take a look at what this is here. We'll draw a line to this corner here from the origin to this corner, and this has some radius r. And furthermore, since the normal is pointing up, and say, like we had up here, the detector is our little patch of area here, then we can see that theta is that angle between that normal vector and that line that goes from the normal vector to the, or from the origin to the detector. So we'll call that theta. But now that's 3D, we have to do one other thing, and that is, let's drop this down to here. We'll draw a line like so, and this is normal. So we have a right angle there, and then we can do the same thing up above. So we'll draw a parallel line up here, and this is a right angle here. And so now we can draw a second angle, and that's between the x-axis and this line that's in the xy plane right here. So we'll call this B. So theta is called the inclination or the zenith angle. And phi is your azimuth angle. So the question is that what is this area here? How do we relate the solid angle, which is this d omega, to this setup right here? And so let's take a look at the area that we have drawn out right here. So one thing that you can see here is that if this is r, is this distance here, and theta is this angle right here. Let's switch off here. If this is r, this is theta, then up here you can see just by doing a simple trigonometry exercise, you can say that sine of theta must be this distance over r, or you could say that this is going to be r sine theta as that distance there. That's the first step. The second step is, since you know that if you have a distance r and you sweep it out over an angle d theta, then the arc length is r d theta. Well, here's our r, and say we were to sweep it out a little bit, a little slice of d theta. So we have theta right here. If we extend it a tiny bit and get a d theta, then that's what this angle will be right here. So this is going to be r d theta. Up top here, since this length of this line here is r sine theta, if we do the same exercise, we have a phi, and say we sweep this out a little bit more in the positive phi direction, so we get a d phi, then the length of the line is r sine theta, and this angle, right, or this length right here, this arc length is going to be r sine theta d phi. So as a result then, this area, we'll call that dA, and we'll put a subscript n because it's pointing normal, or the normal rather, of this little patch is pointing right towards the origin. It's normal to the origin, is equal to the product of the side length. So it's going to be r sine theta d phi times r d theta, or r squared sine theta d theta d phi. And since we know that area, we can then calculate the solid angle. I'll get around here. So solid angle, the omega is defined as dA sub n over r squared. So if we simply take this value of dA sub n and we stick it into there, the only thing that happens is the r squared cancels out. So we're left with sine theta d theta d phi. So that's how you get d omega. So then as we look at this d omega, then we get it in terms of theta and phi. And you can see, if we go way back to our definition of intensity, we see that it depends on lambda, theta, and phi. So in other words, you can have intensity varying in either of these directions here, right? So we theta or in phi. It could depend on all those things. So let's do a quick example. We're going to calculate what's the solid angle associated with the hemisphere. This will be our first example today. The solid angle omega associated with the hemisphere. So what we would do is we have our little patch here, and we have our normal vector like so. Here's our hemisphere, looks something like this. So all we would need to do then is we're going to integrate d omega, and we're going to do so over a hemisphere. So that's my little hemisphere symbol here. So of course, to do that, we need to write d omega in terms of theta and phi. So we're going to integrate then sine theta d phi. So then let's look at the limits here of what theta and phi should be. So phi is the outside one, so we'll start with that. So you can see that phi is defined as this angle that goes from the x-axis down out to this line that represents the plane where r is in. And the idea is that if you have these little patches, you can integrate it all the way around the z-axis, which means that you start at x-axis, go all the way around the z-axis, come back to the x-axis again. So in other words, phi would have to vary between 0 and 2 pi. So then there's theta. And theta, you can see here, is that for a hemisphere, of course, if theta is equaling 0, you're along the z-axis. And the most that you would ever take theta is where the patch is essentially lying along the xy plane. In other words, theta would start at 0 and end up at pi over 2. That's the maximum value there. If it was a sphere, you'd go all the way down to pi. And here we're just going to pi over 2 because we're just dealing with a hemisphere. So now we can integrate. And so first phi is very straightforward since we can isolate it out. Nothing depends on phi in our function here. So we just simply say phi equals 0 to 2 pi of d phi and get 2 pi. So then the theta side is 0 to pi over 2 sine theta d theta. Take another step here. So it'll be 2 pi. And then if you integrate sine of theta, you get cosine theta, actually minus cosine theta. So we have to flip the limits here. All right, and it's 2 pi, and cosine of 0 is 1, and cosine of pi over 2 is 0. So you get 2 pi. And the units for this are steradians. So just like you have radians for a 2D case, for 3D case, you have steradians. So we have SR. And so that's our solution. Right, so a circle has 2 pi radians, and then for a hemisphere, you get 2 pi steradians. So it turns out that for a hemisphere, you get 2 pi steradians. In a sphere, you get 4 pi steradians because it's double what a hemisphere is. Okay, so let me append a page here. So let's go back and talk about intensity a little bit more. So actually maybe now that we've spent time introducing the various elements of intensity, right? So again, when you talk about the projected area, we talked about it being part of the electromagnetic spectrum. So you have a d lambda, and then the solid angle, we have a d omega. We talked about that as well. So let's go back and revisit this using a more formal definition of intensity. So we often in textbooks don't see the equation listed like so. We usually see it written in terms of intensity as defined as dq over dA cosine theta, d lambda, d omega. So we'll do that here as well. So this is generally more commonly seen this way. So you have I sub lambda E, lambda theta phi is defined as a differential amount of heat over the projected area for a little bit of wavelength range over a small solid angle. So if you look at the units then associated with this, with intensity, of course, heat, we usually in SI units do watts. Projected area is just going to be square meters. The lambda, we go back up to our little diagram here of the spectrum. We see that it's used, it's generally listed in terms of microns or micrometers. And then the solid angle is steradians. So let's do a couple of examples here. So let's say this is now example 2. If example 1 is finding the omega associated with the hemisphere, example 2 is for this scenario here. And this is, in both of these examples, we're going to talk about a quote unquote diffuse emitter. So what this means is that your intensity is independent of theta and phi. In other words, it's the same in all directions. So here we are. This is our emitter. And is our normal vector. We'll call this surface 1. And over here, it's facing this way, call that N2. This is our detector. And if we were to map this onto a coordinate system, the emitter would be at 0, 0, and the detector would be at 1, 2. The area of the detector is 10 to the minus 6 square meters. The emitter has an intensity of 1 watt per meter squared microns to radian, an area of 10 to the minus 5 square meters, and then it only acts on a small wavelength range of 10 to the minus 2 microns. So given this, we want to find what's the heat flow from 1 to 2. Okay. So the way you want to tackle this problem is let's start by just drawing a line from 1 to 2. And we know that this makes up a right angle. If we were to close this out, where do we know this would be value of 2, and this is the distance of 1. So use Pythagorean theorem, and what you get is that square root of 5 is going to be your radius r. Okay. And so we need then to define our angles. So this will be theta 1, and this is theta 2. We can tell just by observing our right triangle here that the cosine of theta 1 is going to be 2 over the square root of 5. The cosine of theta 2 is 1 over the square root of 5. So if you look back at our equation for intensity, we're trying to find Q. In fact, probably the easier thing is to go back to here, because this is the more direct equation we're going to use. So we're trying to find this. We're given the intensity. If we need to find the projected area as dA cosine theta, or in other words, it's going to be A1 times cosine theta. So let's take a look at that. So it'll be the projected area. Actually, maybe I'll just write out the equation here, and then we'll just fill things in. So we'll set a dq. We'll say this is finite. So we'll say q1 to 2 is I lambda e times d, and so we'll say A1 cosine theta 1. And then there's the delta lambda, and then there's the omega. All right, so then really we have A1, we have cosine theta 1. So if we go here and check out what we have this, this, and that. So we still need to get d omega. So d omega is, again, defined here, if we go up, as the normal area over r squared. In other words, this is the projected area of the detector as seen from the emitter. So d omega, which is dA sub n over r squared, would be A2 times cosine of theta 2 over r squared. And so we're using the projected area here. So if you're on the emitter and you look up, how much of the detector do you see? Well, you have to take that theta into account over there. So this ends up getting you then 10 to the minus 6. Cosine theta 2 is 1 over square root of 5. And then r squared is 5. All this has units of steradians. So we can stick this into here. And if you do all the calculations, so in other words, you have a value of 1 watt per meter squared micron steradian here, 10 to the minus 5th times 2 over cosine, 2 over square root of 5. You've got 10 to the minus 2 microns, and then you have this value here for steradians. What you get, and it's all said and done, is you get 8 times 10 to the minus 5 watts. Okay. Then the other example I'll show you to finish off the module. Is another diffuse emitter. Down here, here's our emitter. We'll call this again surface 1. So again, there's an N1 here. Out here's a detector pointing down. And this distance here, oops, look out for that again. So between here and here, 1 meter. And then between here and here, also 1 meter. Okay, so here we go. The detector, it reads 10 to the minus 10 watts. From the emitter, the emitter has a range of lambda equals 0.1 plus or minus 10 to the minus 3 microns. The area of the emitter and the detector is 1 square centimeter, about the size of a postage stamp. So after all this, we want to find what the diffuse emission intensity is. I'll say if it's diffuse. All right, so what we're going to do is, again, start by drawing some lines. Let's draw a line from the emitter to the detector. I know this isn't a little bit skewed here. Sorry about that. But the idea here is that you have an area 1 and an area 2. And here there's a theta 1, and here there's a theta 2. So we can use our equation then up here of intensity to get our value down below here. So we can say that I lambda E is going to be Q 1 to 2 over A1 cosine theta 1 delta lambda times d omega or delta omega. One's fine here. Okay, well, we're given a value of 10 to the minus 10 watts, so that's our Q. So we're good with that. We're given A1, so let's find cosine theta 1. So it turns out, as you can see here, that they're both theta 1, theta 2 are going to be the same here because they're the opposite angles between two parallel lines, between N1 and N2. And then draw that N2 here is N2 right here. There. So just by observation here, cosine theta 1 is equal to the same thing as cosine theta 2, which is 1 over the square root of 2, because our radius r is going to be square root of 2. All right, again, using Pythagorean theorem. Great. So we're given cosine theta 1 is 1 over square root of 2. And delta lambda, this is a little bit trickier. And then if you think about this detector here, you have 0.1 microns, and then there's a range here though. There's a of that it's reading. So it's 0.1 minus 10 to the minus 3 over here. And this is going to be 0.1 plus 10 to the minus 3. So your delta lambda is going to be this range right here, or 2 times 10 to the minus 3 microns. Turns out that mean value of 0.1 doesn't matter for this particular example. The area is A1 and A2. Just a minor thing here, it's 1 centimeter squared, so this will be 10 to the minus 4 meters squared. So you want to convert that to SI units. And then finally, d omega, which similar to what we had before, so d omega is equal then to dA sub n over r squared. A sub n is the projected area of the detector as seen from the emitter. So it'll be A2 cosine theta 2 over R squared. And of course, cosine theta 2 we have, A2 we have, and R squared we have. So we were good with everything here. Maybe just to finish this off, I'll just plug in everything just to show you how it all works out. So I lambda E will be 10 to the minus 10 watts over A1 is 10 to the minus 4 meters squared. 1 over square root of 2 is the cosine of theta 1. 2 times 10 to the minus 3 microns is the delta lambda. And then d omega will be A2 cosine theta 2. So 10 to the minus 4 meters squared, 1 over square root of 2. Actually, what I'm going to do is I'm going to get rid of the meter squared because we know that collectively all of this has to have units of steradians. So we'll say 10 to the minus 4, 1 over square root of 2, all divided by 2 steradians. And when you plug all the numbers in, what you should get is 20.2 watts per meter squared microns steradians. And that's it.